Hello, everyone. Welcome to part three. Yes, it is part three or clip three of topic five. So we are still in topic five, where we are talking about knowledge, reasoning, inference, and uncertainties. Today, in this part three, we are talking more about probability theory, and then we can see how to build some Bayesian or some probabilistic reasoning based on that. Let us start. Yes, so we start with some basic introduction to probability theory. So actually, probability theory is a branch of mathematics that we try to put some measure for our uncertainty. So we need to have some quantification, some numbers represent our uncertainty about any event, any uncertain event. So we need to have some measure or quantification for that. Okay, so usually in deterministic life, we talk about impossible. Impossible, that means that probability is zero, or some deterministic, which means that probability equal to one. Actually, as I mentioned in the previous clips, that in our life, we don't have if we go in the details and we took accuracy into account, then we don't have exact numbers, or we don't have probability one for anything except death, as we mentioned before, or uncertainty. Yes, they say that there's only two certain things are the death and uncertainty. Okay, anyhow, now we talk about some math concepts of probability. So probability actually is based on three axioms. Okay, the axiom means that a proposition that is not possible to prove or disprove. So it is truth by assuming it as self-evident or based on some common sense. Okay, so now the three axioms of probability, they are: the probability of any event must be greater than or equal to zero, and the probability of all possible events, it is called like sample space. Sample space is the set which contain all possible outcomes from any experiment. It can be continuous, can be discrete. So the probability of gamma is, or of omega, sorry, is equal to 1. Okay, which means that the probability of any event is always greater than or equal to 0 and less than or equal to 1. So this is the first, like the two axioms. The third one, that if A and B are disjoint events, then the probability of A or B is the probability of, or is the summation of probability of A plus probability of B. Based on these three axioms, actually we can build more, or we can derive more theorems based on that. For example, the probability of omega minus A, if you have sample space and you remove from this sample space some like a certain event in certain this sample space. I am going to give several examples later to explain those things in more details. So this will give 1 minus probability of A, the probability of phi equal to 0. Phi is the empty set. So if you are doing some experiment, for example, if you throw the coin, so actually if you throw the coin, this is the experiment. The experiment is throwing a coin. So in that set, or in that case, what are the set? The set contains only two events, either head or tail. Okay, so what is the probability that you throw coin and you got nothing? So of course it is 0. So in that case, the probability of phi, because it is already, we define existence of experiment, so in that case there should be some outcome from that experiment. Then probability of A or B equal to probability of A plus probability of B minus probability of A and B. This is in case of non-disjoint events. So if the events are joining, or it can have some common intersection between them, then the probability of A or B is equal to probability of A plus probability of B minus probability of A and B. Okay, so here this when it is not disjoint, means that the probability of A and B is not 0. when the probability of A and B is 0, it means that we call them mutually exclusive events or disjoint events. So it means that A and B cannot happen together. So if A happened, then B cannot happen. Okay, so in this case we call it like disjoint events. Like, for example, what is the probability that you throw a coin and then you get head and tail in the same time? In this case, it is 0. Okay, and then probability of A and B is always less than or equal to probability of A or B, and probability of A or B is always less than or equal to probability of A plus probability of B. And of course we can deduce this one from this one already. Okay, and so on. So actually we have several theorems. We have many theorems that we can build over the previous 3 axioms. Okay, so now we can give some demonstration about the probability theorems based on Venn diagram. So this is actually when we have event A and event B, and then we have here probability of this is the A and B, so it is the intersection between 2 events. Here is A or B, so it means that all events in A and in B both. And here the A complement, it means that every element which is not in A but in the sample space. Here is A minus B. So you can see that you can simplify those theorems, or you can visualize them by using this Venn diagrams. Okay, now just to give some few examples of if, for example, A equal to 1, 2, 3, 4, and then B equal to for example, let's say it is 4, 5, and 6, and 7, and then omega is the sample space is 1, 2, up to 10. Okay, so now you can make these calculations easily. So if I asked you what is A intersect B, so it means that what are the elements that they are in A and B in the same time. So in this case, A intersect P is equal to, you can see that the only element that they are common is 4. So it is only one element is equal to 4. If I ask it what is A or B, then all elements they are in A and B. So it is 1, 2, 3, 4, 5, 6, 7. So in this case, A or B or union B is equal to from 1 up to 7. Okay, now if I ask you what is A or B complement, so it means that what are the elements which are not in A or B but they are in the sample space. So in this case, because we have here from 1 to 7, so the left element is 8, 9, and 10. Okay, so these are just simple examples about how to make this from the set theory point of view. Okay, how to compute the probability, how we can calculate the probability, or how to build some measure of the probability. Actually, we have at least 2 approaches, okay, or 2 main approaches. First approach is based on logical concepts, and the second approach is based on long run frequency. Okay, let me explain to you what is logical concept and what is the long run frequency of probability. Okay, now let us have this example before that. We have omega is, we have cards. Okay, we have cards or papers, and in each paper there is a number. So we have the numbers are from 1, 2 till 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have, this is omega now. Okay, this is the omega. What is the experiment? The experiment that we draw one random paper which contains one of these numbers. Okay, so we have this experiment now. Of course, we can project it into many other like physical problems or so on, but let us take it as easy as this one, and just to explain the concepts. So now we have 10 cards. there is printed on each card a number, but it is printed in the other side, so we don't see the numbers, and the cards are not like ranked, so they are randomly distributed. In this case, we are interested to see, so we have some uncertainty. We have some uncertainty about the drawn card. Is it 1? Is it 2? Is it 3? We don't know. Okay? Now assume that we draw the cards without any pre-reference, so we don't have any like algorithm that we do, so it is called blind drawing. So we have a blind drawing of the cards. And now we like to calculate the probability of having any of these numbers. I like to build a logical concept how to have this probability, just based on logical thinking. Okay, we said that probability of omega equal to 1. So the probability, if I asked you what is the probability that when you draw the card, what is the probability that the card number is 1 or 2 or 3 or 5 until or 10? Okay, so what I counted now, I counted all the numbers in the sample space, so all possible outcomes. So you, of course, you will say immediately that it is 1, because we have to have one of these numbers. So the probability of omega is equal to 1. Now, is 1 and 2 and 3, are those numbers are disjoint or not? Of course, they are disjoint events, because if it was 1, it cannot be 2 in the same time. If it is 3, it cannot be any other numbers in the same time. So it can be only one number at a time. So in that case, we can say that the probability of event 1 or 2 or 3 up to or 10, which means that as I said, this is omega, of course, this equal to 1, and this equal to the probability that the drawn card is equal to 1. Okay, so we can call it like, for example, the drawn card number, we can call it like D, for example. So here the probability that the drawn card equal to 1, or the probability of a drawn card equal to 2, plus probability of the drawn card equal to 3, plus until we reach to probability of the drawn card equal to 10. Okay, so this is actually the result. So the result, that why I made it in this way, because they are disjoint events. They are disjoint events. So the summation of these probabilities must be 1. Must be 1. Okay. Now I asked the third question. So now if all cards that we don't have any pre-reference in drawing any card, so if we assume that it is like equally likely process, so it is equally likely process, it is a blind process, so you don't have any trend, or just you shut your eyes and you draw one card. So it means that you don't have any bias in selecting the card that you want to draw. So in this case, if they are equally likely, so the probability of being 1 or 2 or 3 up to 10 will be simply the same. Will be the same, because in this case we don't have any like bias to select the specific card. So in this case, all of them, let's say that they are equal to B, so everyone is B. So in this case they are 10, so 10B equal to 1, and then the probability of each of them will be 1 over 10. So the probability of drawing any of these cards will be 1 over 10. Why? Because they have 10 outcomes, and because they are all of them, they are disjoint events or mutually exclusive events, and also they are equally likely events. So in this case, the probability of each of them equal to 1 over 10. This is based on logical concepts. So you can see that we calculate the probability, we calculate our uncertainty of getting any of these numbers is only based on what? Based on logical thinking. Just in a logical way, or which is based on mathematics. Okay, now we can also compute the probability in different way. So the different way is based on long run frequency. What is the long run frequency? Now assume that I want to calculate the probability that the drawn card is equal to 3. Okay, now by this logical thinking, it gives us that the probability of that the drawn card equal to 3 is 1 over 10 or equal to 0.1. Okay, now I don't make any thinking in this way, or I don't build any math, but I just want to check this myself. So how to do? I bring the cards, okay, and then I draw one card. I see if this card is equal to 3 or not. If it is not 3, then I increment some number like n equal to 1. Okay, and we have another number is NE. NE is the event. So if I got the card number is 3, I will increment also NE. If it is not, I increment only the general counter N. Okay, now I draw the second number, so it was not 3. So then this number becomes 2. NE is still 0. Then I draw the third number. So the third number, let's say that it was 3. So now I increment this to be 1, but I increment also that general counter. So now it is 3. Okay. Then I draw the other number, like for example, it was 7. So it is not 3. Then this number becomes like 0. So I don't make any increment for the NE, by I increment this number to be 4, and so on. So in this case, we call it like long run frequency. So now then let us see how those both algorithms are to be. So now this is the logical approach that as I mentioned. For example, if we throw a coin 3 times, for example, then this will be the sample space. So the sample space will be head, 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 tail, up to tail, tail, tail. So we will have 8 outcomes. So this is the sample space. And now if I asked you what is the probability that the second coin landed head, then this will be this one, and this one 2, and this one 3, and this one 4. So we will have 4 outcomes that it will be with this second coin landed head. And in this case, the probability of having this event E will be half. So because we have 4 out of 8, every one of them will be 1 over 8, 1 over 8, 1 over 8, and 1 over 8. So the total will be half. So the probability is 50%. This is based on the logical approach. Based on the long run approach, then as I said, so you make this realization of this experiment. So it is based on data, actually. It is based on data. So you have realization, you make this experiment, or you make emulation for this experiment. Sometimes let's say that we have like a power plant or power system, so we cannot make direct testing for this big plant, but we can make some emulation for the plant, or so also it is called simulation. But emulation means that we represent every equipment in that power system with some like mathematical model, and then we run the whole system. Then we can make this calculation of probability of certain event. For example, what is the probability that this smart grid or this power system will collapse based on some like cybersecurity attack, for example. Okay, so in that case, we can make such kind of simulation to see how the effect will be. So the long frequency approach is actually much more easier in case of very complicated systems. So in case of like just throwing a coin, or you have cards, or you have such kind of basic example, actually we can easily make this logical approach, and we find the probability, like the exact probability of that. But if you have like much more complicated system, then it is hard actually to compute the probability by logical approach. I give you another example. If the example of even the example of drawing this card that I explained before from 1 up to 10. So if the person or the process which draw a card every time, it has some hidden like algorithm. So it was not selecting the cards in completely blind way. So it was using some kind of blind trick or a blind algorithm or a blind logic that you don't see it, and they selecting the card in according to certain sequence or according to certain approach. But this approach is hidden. So now, because we don't have any knowledge about the process, so and if we say that this is equally likely, then I will say that the probability of getting a 3 is always 1/10. Okay. However, maybe if we make this experiment and we run this for very large number of timers, maybe we find that it was not 1/10. Maybe we can find that the probability of getting a 3, it was approaching, let's say, maybe 3/10 or 4/10. So what that mean? When it is approaching 4/10, it means that it is biased toward 3, because it means that the whole other numbers from 1 up to 10 without 3, the rest, they have the probability of 6/10. And it means that 4/10 will be for the card 3. So it means that the algorithm which is generating these cards, they're using some kind of hidden process that we don't know. But this will be discovered by using this simulation. Okay, so by using this simulation, or by the long run frequency, we can find some hidden numbers there. Okay, so this is very important to remember about the two two common ways to calculate the probability. It is logic based or long run frequency based. Okay, now we can see here that some comparison between two approaches. As I said, that the logical approach is not always possible to do. However, if you have like very accurate model about the process and it was easy to represent, of course, logical approach gives you more accurate result, because the long run frequency, it needs to be run very large numbers of times, or very large number of times, in order to find the probability, especially if the probability is very small. If you are looking for something which is rarely happen and you want to compute its probability, for example, if this thing is the probability of to happen, that it is 10 of the power minus 6. So every 1 million times there is a chance to appear only once. Okay, so in order to calculate, it is according, or it is like in this range of numbers. So in order to get like good estimation of this probability, so you need at least to run this experiment like 10 divided by it is estimated probability. So if it is estimated probability is 10 of the power minus 6, it means that you need to run this experiment like 10 million times. Of course, it doesn't mean that it will be very accurate, but in this case, if you want very accurate, maybe you will need to run it like 100 divided by b, which means that it will be 100 million times. So just imagine about very complicated system with thousands of parameters there, and you need to run this like 100 million times to calculate the probability of certain event. What is the like uncertainty level to happen? Okay, so this can be like it might take very long time. So if you can find some like logical approach way to estimate at least the probability, this can help in many experiments. Of course, we have also some other like tricks that we can do to reduce the number of computation, but we will not go in the details of that. Okay, so now logical also here, of course, just a continuation about the differences between logical and long run frequency. Here we give another example about medical. If you are in a country that there is no like record about certain disease, for example, if what is the probability in this country that young people from 20 to 25 years old that they have diabetes. Okay, so now we want to calculate the probability of this. So just think that how could we build logical approach. So in logical approach means that we can go deep into genetics, like the genes of the people living in that country, and what is their like exercises habit, food habit, and many other things that we need to find in order to build some logical approach to based on math. And we can say that it is very complicated, even it can be impossible. But what is the easier approach? The easier approach is to start having like making some taking blood test, or asking people randomly, taking some sample number. It is a random sample, and there are some conditions how to select this sample. And then we for example take 20,000 people in this age interval, and then we check if they have the diabetes or not, and based on that we can have some estimation. And this estimation is based, because why we say estimation, because for example, if you have 20,000 people and then you find, for example, 500 they have diabetes in this age, so we will say that the probability is 500 divided by 20,000. But actually this probability is the probability for this sample, and this sample is not necessary to be very accurate sample to represent the whole like population. So in order to have exact the number of the chance that anyone from within this age interval to have diabetes, actually we need to have the whole population to make the measurements and or to make the test. Of course, this is not usually possible, because maybe the country they have like millions of populations. So in that case, we rely on this 20,000, but we will have what is known as confidence interval. So we have confidence interval that the real probability or the uncertainty level to have diabetes in this within this age interval, it will be that probability. So we can say the confidence, with a confidence interval of 90%, that the probability it will be like greater than or equal to, let's say, 0.05 and less than or equal to, let's say, 0.1, for example. So we can say that this is 90% with confidence to that the probability between these numbers. So how to build this probability is based on the sample size and also other conditions. This is very well known in statistics. Okay, so here we have a few examples, but we are not going to explain all of them. You can find them in the slides, so please go through them. They are very simple examples, very similar to what I was explaining now. Yes. So for example, here what is the probability that you if you throw two dice? So every dice, it has, the dice that it has six faces. It has 6 faces this way. Okay, so we have 1 face, 1 point, 2 points, and 3 points, and so on. So it has from 1 up to 6 faces. And then what is the probability what is the sample space if you throw 2 dice? Then it will be from 1 up to 6. Okay, now if we ask us what is the probability that the sum of dice equals 9, then we can build the event. Remember, now we are thinking in logical way or logical approach. So we build the event. So the event here is the number is 9, is 3 6, 4 5, 5 4, and 6 3. This is the all possible outcomes that the sum will be 9. So it is 1 2 3 4. If all outcomes are equally likely and we have 36 outcome, then the probability of each of them will be 1 over 36. And because they are mutually exclusive, they are disjoint events, it means that no 2 events could happen in the same outcome. So in that case, it will be 4 divided by 36. So 36. So it is very easy that to find. Okay. Of course, you can make this the same experiment. Actually, you can, if you repeat it so many times, then you are making the experiment, these experiments in equally likely, then you will approach this 4 divided by 36 on, if you repeat it many times. Of course, this limit is on probability sense. We are not going to or it is called on the mean square sense, but we are not going to in the details of this. Okay. Yes, here we have another example. So samples can be also continuous, as you can see. For example, it can be from 0 is included, and up to infinity, or it can be between 4 and 8, and between 4 and 8 we can have infinity number of events, because it can be 4.00001, it can be 4.1, it can be 4.2, it can be anything in between 4 and 8. So here we have continuous interval. Continuous interval, it means that it has infinity number of like individual numbers, but we have here interval. Okay. Yes, now we came to the most important part in this probability related to our subject, is the conditional probability. And then we go to the Bayesian theorem. But let us stop here and we take this in the next clip. Thanks a lot.